Okay, we talked about shapes of molecules with all the different different numbers of pairs of electrons, all the possible shapes. Now, what happens when you've got a double bond? The short answer to that is you treat a double bond as though it's just one pair of electrons. You just treat it like a single bond, and the reason for that we'll explain. But if you think, right, there's ethene, and I've drawn the dot cross diagram for ethene, so there's no lone pairs in ethene, and we know the shape of it. I think we've talked about pi bonding before. When you get a double bond, you get so here's the carbons. So one of the parts of the double bond is the sigma bond, which I'll draw there. Okay, and these are all sigma bonds to the hydrogens as well, and they're all flat. It all fits on the same sheet of paper. We mentioned that before. Now we can see why it's all going to be flat in a minute. But we do have a pi bond as well to worry about, and that's like the banana thing, isn't it? Above and below the plane of the molecule. Now, the combination of the pi bond is vertically above the sigma bond, so you just treat it as one. You just treat it as one thing, right? So, and that's why it doesn't have any effect on the shape of the molecule. Okay, so the repulsion between all of those three things I'm just drawing in purple there is all the same. So effectively, you've got three pairs there, haven't you? Three bonding pairs. And we know what shape you get with three bonding pairs. It's trigonal planar. So now we know why. Okay, so that carbon is carbon on the left is trigonal planar. The carbon on the right, the geometry around that is also trigonal planar. So the whole of the ethene molecule is flat. All of the atoms will fit on one sheet of paper, on one plane of paper. All the bond angles are 120. Okay, so that's what happens when you have a double bond. Just another really important example. Let's talk about carbon dioxide. Okay, so carbon dioxide. Right, there's no lone pairs there. Just very quickly draw a dot cross diagram, shall we? Carbon, so a double bond here, dot cross, a double bond here, dot cross. There's the oxygen, two lone pairs on the oxygen, two lone pairs on that oxygen. Looking at the carbon though, we have got, what have we got? We have got, we treat the double bond like a single bond, so we have got two bonding pairs. It's the same as that, okay? So what shape would that be? Two bonding pairs, it will be linear, and the bond angle will be 180 degrees. So carbon dioxide is a linear molecule, and that's really important. Do you remember we said about symmetry and dipoles earlier on? So that's because it is linear. Well, this carbon, there's no dipole, even though this carbon has got a delta minus on it, because, sorry, this oxygen has got a delta minus, because this one has got exactly the same delta minus on that. So because it's symmetrical, because it's linear, no dipole on carbon dioxide. Right, let's just do a couple more examples. I'm going to do sulfur dioxide and sulfur trioxide. Okay, do SO3 first of all. Right, the dot cross diagram for that. Right, so what you've got is you've got three double bonds. You know it's got to be that, because sulfur can form 6 bonds. Oxygen only ever forms 2, so it's got to be like that. So there we go, here's sulfur. And the oxygens all have 2 lone pairs. I'll just do it on that one. But you can see the main thing there is I've counted up for 6 electrons in the sulfur. There's 6 crosses there. Sulfur's in group 6. So all sulfur's electrons are accounted for, so there's no lone pairs. So all we've got treat the double bonds like singles. We've got 3 bond pairs. So what shape is that? 3 bond pairs, no lone pairs. It's trigonal planar. And the bond angles are all going to be 120. So sulfur dioxide would be a flat molecule. Let's do sulfur dioxide. That's quite interesting. Okay, so sulfur dioxide. Also, yeah, look at sulfur trioxide. No dipole there, because yeah, oxygen is more electronegative, but you've got symmetry there. There's no dipole on sulfur trioxide. Sulfur dioxide. Well, sulfur dioxide is like this. You've got 2 double bonds. Okay, so here's a double bond. Here's a double bond. Okay, now sulfur, I've only drawn 4 electrons for sulfur. It's in group 6, so that means we have got a lone pair there, which is going to make a difference. The oxygen, they're in group 6, so I need a lone pair there, lone pair there. Same with this one. So what have we got here? We've got 3 bond pairs, but, sorry, 3 pairs, not bond pairs, because double bonds you just treat like single bonds, 3 pairs. But we've got 2 bond pairs and 1 lone pair. Well, what's going to happen here? Well, we have got, I'll draw the lone pair on there, yeah, we've got a lone pair. Now, that is 3 pairs, it's always trigonal planar is the basic shape, isn't it? So that will fit on one plane, but that's going to push these back a little bit. So that means the bond angle here is going to be not 120, it's going to be more like 118. And interestingly, sulfur dioxide will have a dipole, because you can see it is not symmetrical, because you've got this lone pair up there, and so it's more negative over this end of the molecule. Yeah. So sulfur dioxide, unlike sulfur trioxide, does have a dipole. So that's just a brief discussion of the effects of double bonds, or how they affect the shape of molecules. And the rule is just treat them like a single bond and proceed as normally. I think I'll just do one more, because I like this one. I'm not going to draw the dot-cross diagram. I think we mentioned sulfuric acid. Sulfuric acid has, yeah, in one of the earlier videos, sulfuric acid is like that. That's concentrated sulfuric acid, and it loses those 2 H's as H pluses when it forms, when it's in aqueous solution. It forms a sulphate ion. So you've got SO4 2 minus, you've got a minus there and a minus there. That's the sulphate ion. Right, you can draw the dot cross diagram for that, but you can see there are no lone pairs when you draw it. No lone pairs. So what have we got there? We have got 4, essentially we've got 4 bond pairs. So what shape is that going to be? It's going to be 4 bond pairs, it's tetrahedral. And what the bond angle is going to be? 109.5. Okay, let's leave that there.